Okay, so we talked a little bit about the film that's covering this hoop house or greenhouse, and some of the other things that are important in energy management are insulation. The two end walls, the first one we already talked about, that's common to the house, and we don't really have any energy loss there to speak of. The other end wall is on the west side of the house, west side of the property, and it is framed with 2x4 construction, just like you would frame your house with. It's made out of redwood, and it has a concrete foundation with concrete block 2 courses high on top of that, and then a vapor barrier, and then the construction out of 2x4. The bottom half of the wall has the styrofoam ball insulation that's 3/4 of an inch thick. The top half of the wall has the polycarbonate panels, corrugated polycarbonate panels. So we'll talk about some of the things that we did right and some of the things that we can improve on. The styrofoam insulation is fantastic. It has almost an R4 insulation value. The polycarbonate panels, not really to be recommended in a greenhouse where you're trying to conserve energy. What we found is that because of the energy loss, they're always cold. They radiate heat out, and they don't have any kind of insulation against conductivity, so they're always cold. This is a high humidity environment, so the panels being cold collect a lot of water via condensation, and they're constantly dripping tons and tons of water. So what we found is that we're starting to grow mold on our redwood. We used redwood because we thought it would be pretty resistant to mold, rot, deterioration, etc. Definitely didn't want to use CCA, pressure treated, but we found that it's growing mold pretty prolifically. We left it on here for this segment so that we could see it, but we're going to be treating that with some essential oils from
doTERRA oils.
doTERRA oils to try to inhibit that mold, bacteria, any kind of growth that's going on there. Right now, we can take a look at it and you can see there's mold growing on it, but that's one of the things that could be improved on. The polycarbonate panels, definitely not a good energy choice. They don't have nearly the R value that either a multi-wall polycarbonate panel or a multi-wall film or a Solex or anything like that would have. So kicking around what we're going to do to change that and make it better. This whole thing is about experimentation and growing, learning, and we didn't do everything right the first time, so we're kind of happy about that actually. So anyway, that's our main energy loss point. Some of the other things that are really important for energy management are capturing the sun's energy when it comes in. So what we want to do, the energy comes in, we want to catch it during the day. And as we catch it, we want to take it out of the air, because the air inside this greenhouse tends to be way too hot during the winter. Just to give you a reference point, this is Albuquerque, New Mexico again. It's been averaging about 20 degrees at night, low 40s during the day. And if we're not running any of our systems, we're looking at 125 degrees inside this greenhouse. The plants hate that, the beneficial insects hate that, and I hate that. It's terrible. So we need to either open up a door or do something about it. So what really helps in mediating the daytime temperature is the same thing that really helps in providing heat at night. Because what we want to do is keep a 50-degree minimum ambient temperature inside this greenhouse at night, and we want to keep a 50-degree or better minimum temperature in the soil at night. So to do that, we need to put energy into the soil. That energy comes back out at night, keeps the ambient temperature warm as well, but the main thing that it does is keeps the soil warm, and that's what the plants need. If you're talking about growing things like tomatoes peppers, eggplants, squash, any kind of what you would normally grow in a garden. Most of those things are warm weather. They like higher temperatures. The green leafies, they'll do well at considerably lower soil temperatures and ambient temperatures. But any of the summer stuff that I just mentioned, you got to keep your soil temperature over 50. I don't know the exact number, but I do know from experience it's got to be about 50 plus, and 60 is great. So what we're doing to capture that heat during the day and put it into the soil is we've implemented two systems. They're both experimental, and we were trying out two different ways of doing it to see which worked best. One of them I just kind of came up with on my own. The other one we pinched off of YouTube. It's not my idea. Great idea. I don't know who to give credit to, or I would, but it's a fabulous idea. We'll talk about that one first. If you look right behind me, you'll see that there is a 4-inch black corrugated tube running up the wall. And the top of that tube is, relatively as high as we could get it, so that the heat that's rising, it's going to be hotter in the top than it is in the bottom because of stratification. So it's pulling hot air. We've got a fan on the other side of that tube right there. That fan is rated at about 120 cubic feet per minute. I think it's about, are we still running?
Yes.
Okay, I think that fan is 220 cubic feet per minute. So it's pulling probably, effectively about 150 cubic feet per minute.
I was thinking 265 or something like that, if I remember, wasn't it?
Yeah, I'm not sure.
That's close enough.
Close enough for the kind of stuff we do. So it's pulling about 150 cubic feet per minute, more or less, of really hot air through that tube. And that tube goes down that wall and it loops around 1, 2, 3, 4, 5 times through this little raised bed that we have right here.
2 foot deep, right?
2 foot deep. And then it returns over to this fan over here. That fan is sucking on that. It's pulling hot air in, and it's blowing out relatively cooler air. When it's pulling in air at about 90 degrees, it's blowing air out at about 68, 70, 72, something like that. I'm not exactly sure about the numbers, but from some of the numbers that I've kicked around with my nephew, who's an engineering student, has taken thermodynamics, we think that we're capturing somewhere in the neighborhood of 45 to 55,000 BTUs per night. Okay, we'll get back with you guys on that and give you a real number, but it's roughly 50,000 BTUs per night, which, if you live in a 2,000 square foot home, you've probably got somewhere in the neighborhood of 100,000 BTU per hour furnace. So that's kind of equivalent to running that thing half an hour nonstop. Might not sound like much, but it is significant. It means the difference between vegetables freezing and vegetables
Thriving.
Thank you. Yeah, and our vegetables are thriving. So that's one system. Thanks whoever that was that invented that. Get back with us and let us know. We'll give you credit. I love it. It's a fantastic system.